So I kind of want to go over the questions, the homework first, so that we can all get a nice little structure on how pointers work. And if you guys remember the lecture from last week, how many of you guys have already completely forgotten the pointers and memory addresses? Anyone? It's kind of like a lot of stuff to go over. It's a little fuzzy.
I need someone to explain it more clearly.
Yeah, it's this is the kind of stuff that will take some time to get over, but I think it's really important to understand the reasons why pointers are useful, as well as how internally pointers are working. To that effect, all these questions kind of ask about how you use pointers and how you declare pointers. So let's just start with let's just go with number 1 here. I'm just going to make this thing bigger. Okay, so number 1 was just how do you declare a pointer? Like what makes a pointer a pointer? In C++, the way a pointer is declared is with the asterisk. So when you put an asterisk in between the variable type and the variable name, that means that that variable now is a pointer to something of that type. So in this case, the correct answer being D. This is, and you can call it several ways. This is a pointer to an integer named x, or x is a pointer to an integer. Either way is fine. Or you have an integer pointer. The important pieces is that the variable name and the variable type are the same, just like any other variable. You just happen to have an asterisk in front of it. Any questions on that? Yeah.
Yeah, I read in the book that the white space in between the integer doesn't matter.
Yeah.
As an asterisk, like it's kind of style. Like I guess they say new modern C++ people will put it towards the integer.
Yeah. So
C people will put it towards the.
Yeah, you can declare it anyways. Here's one way.
Yeah.
This is not a good way to declare it. This makes it look like it's integer times x.
Right.
So like you say, there are. So what Overwatch uses, what we use for our coding standard is this.
Yeah.
Because the way we reason is that it's an int pointer, not an x pointer. Mm-hmm. So it's all the same. It doesn't really matter if you put the white space here or here. It is exactly the same. But the reason why we tend to favor putting the asterisk to the left of it is because it much more clearly associates what that thing is. It's an integer pointer, right? And it's more style at a certain point. But like this is exactly the same. It's still an integer pointer, but when you're reading it, you kind of tend to group the x and the pointer together. Yeah. It's not a pointer x. It's an integer pointer. So when you're reading from left to right, that makes a little bit more sense. So yeah, just we follow this. This is our coding standard. So it hasn't either way is fine. But if you want to use a coding standard, then this is probably the better way to do it. Questions? All right, so let me just color code this thing green so we can actually all see it.
If you hit the little highlight thing, it makes it way clearer.
Oh yeah, good point. I'll do that. Okay. Now you guys can't read it. I can read it fine on my monitor.
Make it yellow.
The yellow one? All right, cool. All right, so number 2, which of the following gives the memory address of the integer variable a? So this has nothing to do with pointers, actually. Number 2 is, even if you don't know what pointers are, number 2 you can still answer. And the reason is that I kind of introduced 2 new symbols to you last week. One was the asterisk, which is how you declare a pointer, and the other was the ampersand, which is how you represent the memory address of something. So remember that spreadsheet that I created last week of how I had the row of all your memory in your computer and then what's inside the memory? So the ampersand lets you get what the address is of a specific variable, which means where does it live in your memory on your computer, which means when you want to get the address of something, you put it before the variable name. This. So the key here is that I'm not declaring a variable. You don't declare a variable like this when you want to get the memory address. This is like, hey, I have a variable a. Maybe it stores a number like 12 or something. If I want to get the address of where that variable lives, then I put an ampersand in front of it when I'm using that variable. So if I'm about to do cout on the variable, that's when I put the ampersand in front of it. Any questions on that? All right. Which of the following gives the memory address of a variable pointed to by the pointer A? So this is kind of a little bit of a trick question because pointers by themselves, what do they store? What does a pointer actually store? What is the only thing a pointer can store? Memory address, right? So like when you want to get the memory address of a variable pointed to by pointer A, what is it really asking? It's asking what is pointer A pointing to? That's what it wants to know, which is just this right here, right? That's all pointers do to store memory addresses. Okay. Now, pointers, they only store memory addresses. That's the only thing that they can store. They can't store anything else. That's almost 100% true. Just for all intents and purposes, for this class and for next class, all they store is memory addresses. There's ways that you can hack around it to store more than memory addresses. You can technically store anything anywhere when you're programming. So whether how valid that is or how invalid that is, that's kind of a more of an advanced topic. I won't get into that. But just if you do happen to dive deeper into that, know that there are things you can do to make pointers do other things if you want them to. But for all intents and purposes, pointers just store memory addresses. So number 4 is asking, how do you get the value of what's stored at that memory address? So if a pointer only stores memory addresses, how do you actually get the number, like the data that's associated with that lives at that address? What is the operator that you use? Yeah. So if you put an asterisk in front of a pointer, and this is the part that always confuses people, and it confused me for a long time. If you put an asterisk in front of a pointer, what actually that means is that, hey, I have a memory address. That's what A points to. That's all. A just points to a pointer. If you put an asterisk in front of it, it's called a dereference operator. It'll say, oh, well, I know you only point to memory addresses, but tell me what actually is living at that memory address. Give me back the data that lives there. What's the funny part, and I don't really know why it's done this way, but this asterisk here has these two operators are completely different. Even though they're the same character, they're completely different operators, okay? This operator might as well be like an @ sign or something like that, something completely different than how you declare a pointer. And I want you to get this distinction in your head because it's really important to understand that when you put an asterisk in front of a pointer, it actually means just dereference, get me the value stored at it. And if they had made it something like a hat symbol, it would be a lot more clear that those two things function completely differently, right? This thing here is saying, hey, I don't want to declare a pointer to an integer. And this asterisk here is saying, all that's saying is dereference. That's what that operator is called. So I know it's easy to kind of group them together and kind of get confused, but understand that this in front of a variable by itself is dereferencing it. And when you declare a pointer like this, you have a variable type in front of it, and that means int pointer. You can almost kind of like group these. This is like one piece right here. Like this variable type with the pointer is just one piece, like almost like its own variable type. It's just an int pointer, and this is a custom operator. Okay. It's kind of like it's very similar to the memory address operator, except instead of getting the memory address of something, you're actually getting the value of it. And this thing only works if it's a pointer type. So if it's not a pointer, you'll try to dereference something that's not unaddressed, which means this only works with pointers. I will say that this operator from number 2, the ampersand, which gives you the memory address, works with any variable. Okay. Which of the following is a proper keyword or function to allocate memory in C++? So the answer here is new. There are ways to the C style of allocating memory is malloc. So we will not really go into that too much. Understand that means memory allocation. So that is kind of the original way to declare memory. In C, you might actually see this in programs show up. So if you're looking at like source code for some game or something, you might see malloc, and that represents the same way you're allocating memory, but it's slightly like a kind of an older way of doing it. Not necessarily worse or better. That's just the style that was done before. Okay. C, what is the following keyword to delete or to deallocate memory? It's going to be delete in C++. Likewise, in C, the corresponding keyword is free. What's that?
For some reason, I don't know why on those last two questions I put it like if I was doing C.
Yeah, free and malloc are the C style way of doing it. Okay. For every one of these that you declare, with every time you call new, you have to be calling delete somewhere in your program. Otherwise, you run into memory leaks. I kind of showed that to you guys last week, how if you just keep calling new over and over again, eventually your program starts using like 10 gigs of memory and never freeing it. So that was a kind of an extreme example, but that's how it works.
Was that when you were trying to crash the computer?
Yeah, exactly. Okay, number 7. How do you declare an int pointer called Pikachu? So number 1 already kind of answered this. You can declare it any way you want, really, but I'm just going to use this in this font here. Like that. Now, how do you dereference Pikachu? Remember what the dereferencing means? It means get the value of that pointer. So if I do like that. Does that make sense? That's what dereferencing means. So if int Pikachu is a pointer, putting an asterisk in front of it will dereference it. For example, let me just give you a little bit more context. So if I were to do this, so I'm going to have another integer variable. I'm going to set Pikachu to 42. The Pikachu pointer will be equal to the memory address of Pikachu value, right? This is how you would like use that pointer. So down here, this and this, you can do both. Remember what the difference is between this and this. Which one of these lines will print 42? The top one will print 42, right? The second one prints out the memory address of what Pikachu value has. Okay. Remember, this is used when you're trying to get at the variable. Remember, like this is a completely different operator. It's a dereferencing operator. So keep that in mind. All right. If the value of Bulbasaur is 21, and the address of Bulbasaur is 400. What is the value of Charmander and Pikachu? So, sorry for the Pokemon names. I thought it would be a little bit better than Tom and Jane. It's a little weird to say Charmander. So, Bulbasaur is 21, and the address of Bulbasaur is 400. So, this number here represents 21, and this one represents the memory address of that variable, which happens to be 400. So what is the value of Charmander here? Well, I'd like to just substitute the values just to see. So the value of Bulbasaur is 21. So this one represents the value. And the memory address of Bulbasaur is 400 because what I'm doing here is I'm grabbing the address of it. So I know I can replace it. So Charmander and Pikachu are those two. All right, another one. So Bulbasaur is 21. But the address of Bulbasaur is 1500, and the address of Pikachu is 400. What is the value of Charmander after that? So this is a little bit of a trick question too. So let's just go over line by line. We can do you can do these replacements in your head, but if it helps you, just do the replacements like right there while you're writing it. So the address of Bulbasaur is 1500, which means here it's getting the address of the address, so this is 1500. And I'm going to put a little like 0x just to represent that it's the address, 1500, just to make it a little bit easier. And the address of Pikachu is 400. What is the value of Charmander? So the address of Pikachu being 400 is kind of a red herring. That doesn't really mean anything. All we're doing is we're copying over memory address into here. So here we're dereferencing the memory address, we're dereferencing Pikachu. So we're getting the value of what's stored here. What is the value of what's stored at that memory address, 1500? It's 21. How do we know that? Because this 21 lives at memory address 1500. So that means when we're dereferencing 1500 here, remember this is what Pikachu is. When we're dereferencing memory address 1500, we get the value. We get the value of what's stored here, which happens to be 21. Okay? That's what that means. Okay. All right. Here's some fun ones, okay? Did anyone try writing these programs to see what it prints out? Anyone? Okay. Let's go over. You should be able to reason out what it is. There's a lot of like asterisks and ampersands being thrown around. The important bit is don't try to read it all at the same time. Go line by line. Like really understand every line before you move on. Programming is it's all in the details. If you skim over anything or you skip lines, you cannot hurry through. I'm looking at you, King. You gotta like read every line one at a time. It's not like reading a book. It's not like it's like more like reading a technical manual. Every detail is super important. In fact, there are contests out there that the whole point of the contest is to write code that is really hard to read and try to understand what that actually is doing. It's called the obfuscated C contest. So it's a way that people write code that's really hard to read. So here we'll go line by line. So it looks like we have an integer variable, a, that's equal to 10. Okay. We have an integer variable b that's equal to 20. Then we have a pointer, I'll make this style, to an integer called p1. All right, so p1 is getting set to the address of a, which means p1 is pointing to what a has. All right, so p1 right here is equal to essentially what it's pointing to the a variable, the memory address of what a has. Now, we're dereferencing pointer 1, which means we're getting the value of what's stored at A. Right here, we're dereferencing that. Okay. What is this value here? Right here. It's 10, because that's what it's pointing to. A. So what's interesting is that when you dereference it, you can do it on the left side or the right side of equal signs. You can. What this means here is that, okay, give me the value of what's stored at this memory address, but I'm going to change it. So I'm going to change that value, which is what he's doing here. So when he does this dereference p1 equals 5, he's actually changing what a is. Okay? And I think I need to kind of draw this out in a spreadsheet a little bit just to show you guys a little bit more. Do you guys have any questions before I jump in? Okay. So I'm just going to write this out in a spreadsheet form because I think it's actually pretty interesting. So I'm going to do variable name here. I'm going to do memory address and value. Okay, you guys can see that spreadsheet. So the variable name, I'm going to A, B, and P1. Okay. So I'm just going to make up a memory address here because we don't actually know what it is, but I'm just going to pick like 1500 here. And this one will be 1504. And this one will be, I don't know, 3500. What else? Okay, who can tell me some of these values? Let's do this together. What is value of A? 10. What about B? 20. What about P1? Who said that?
OX 1500.
Who said that? Okay. How do you know it's OX 1500?
Address of the.
That's the address of A. Okay. I'm going to color code these. Each color represents a different memory address. So this one here, that's what it's pointing to. Keep in mind this is the value column and this is the memory column.
How come the P1 value is like the memory address?
Because P1 is a pointer. Remember, pointers can only store memory addresses in their values. That's all that pointers can store. They can't store anything else. They can't store numbers or anything like that, with exceptions.
So, in on number 11, when it says pointer P1 equals 5, is the equal 5 just kind of like a bullshit number? Or
It's not.
what's 5 really?
So he's actually changing the value that's stored at that memory address, which is what I'm about to show you. So this one here. So if I got rid of this for now. So this line that I've highlighted right here, P1 equals address of A. As soon as he does that, this shows up in that pointer, right?
That would equal 10. Right?
Yeah, so you see here that at that memory address, the value is equal to 10. Right, do you see that this thing?
Yeah.
Let's see. The value of that is equal to 10. So this line, I'm just highlighting in yellow the lines that we have basically run in our head. This line right here, what is happening? Asterisk P1, dereference P1, and set it equal to 5. So the value of P1 is this, right? When you put an asterisk in front of a pointer, you get the value of what's stored in that pointer, right? We just did this above. When I put an asterisk in front of P1, it actually says, oh, well, whatever's stored at this address, give me the number that's stored there. So what is this going to give you?
It's going to make the value of, maybe I should, it's going to give you the, P1's going to become the value of A, and then you're going to set P1 and A to 5.
Wait, you're jumping ahead. I'm just asking what actually happens when I dereference P1, right? So here are all the memory addresses of it.
That's what I said maybe.
This is what the value of it. Going back to the original problem, remember number 4? Which of the following gives the value stored at that address? Given by A. So when you put an asterisk in front of a pointer, it gives you the value at that address. Which means when I put an asterisk in front of P1 here, it gives me the value stored there. So it says, hey, at whatever stored at this memory address, give me the number. So it's going to be 10. It's going to give you that number right here. So the important thing, though, is that when you dereference a value like that, and you say, hey, whatever that value is at that memory address, which is what this means. This means whatever the value is at the memory address pointed to by P1, whatever that value is, which happens to be 10, set it equal to 5. Okay? So what he's doing right here is that he's taking this 10 and he's changing it to 5. He actually changed what A is right there. Okay. Does that make sense?
Yeah.
So that's what this line is doing. So let's do another example. He's about to do this to B as well. So now he's saying, hey, P1, point to the memory address of B. So this becomes that. Okay. That's what P is pointing to now. Okay. Then he's saying dereference P1 again and set equal to 10. So what's changing to 10 here?
So 20 is now turned into 10?
Yes. Because of this line right here, he's setting whatever's pointed to at this memory address set equal to 10. Okay. So now what is the next two lines? What are the next couts print? What does it print? Now you can see 5 and 10. And this is kind of the crazy part about pointers, is that pointers can kind of like, from far, kind of like a distance, change values of things that it's pointed to. So you can grab, and these used to be 10 and 20. He didn't change A and B at all. He just changed the values pointed to in that pointer. Okay. Questions? You guys need another example?
Is it used for like trying to transfer a character or something?
So this style, like understanding how pointers and pointing to memory addresses work, is important because when you're passing around like a hero in Overwatch, let's say, and you have one hero, like Tracer. Let's say you're Tracer in Overwatch and you're running around, and I want to deal damage to you. What ends up happening is that what you do is you pass pointers around the code to Tracer, and you're like, well, this character I want to deal damage to her. So what you do is somewhere else in the code, you're pointing to tracer, and you're saying, hey, change her health value. And what you're doing is exactly what we're kind of doing here. You might be like in a completely different file. You might be in a completely different function, but you want to change the value of her health. And that's why pointers are important, because you can't just, it's actually not like possible to just take tracer and pass her around the functions from function to function. The only way you can like pass an object like that is via pointer, or what we're about to go over next week is when you have a function, you can pass a pointer to it, which will pass tracer around. There's another way you can pass data around, which is passing by reference, which we'll get into next week. But more commonly, you pass a pointer around because you want to, a tracer is huge, for one thing. Also, when you're calling functions, you don't know what they're going to do to it, so you're just like, here, have tracer do whatever you need to, give her health, deal damage to her, have her jump, whatever things you need to. And all those things, like health, this could just be health, for instance. And this could be maybe mana. And maybe a good example here is Pokemon. Maybe this will be my Pikachu. And this will be Bulbasaur. And then this one will be current Pokemon. So an extreme example is this is the same exact thing memory addresses. So Pikachu, the value of Pikachu actually has several pieces to it. Pikachu might have like health is equal to 100 and level equals 12 and attack equals 30. Right? Those could be his values. And maybe Bulbasaur has something like okay. And so what you usually end up doing is you have a pointer to a Pokemon, and you pass this pointer around. And this pointer is just a memory address. That's all pointers can store, is just memory addresses. And when you grab this pointer and you change like Bulbasaur's health, you're changing what the original Bulbasaur had. So if I were to take this memory address and be like, oh, let me change the value of health to be 150, I do it via this pointer here. So I can change the value of Bulbasaur's health. We're going to get into more of this example, but maybe I can show you guys. This is really, I think the true benefit of pointers comes when you're dealing with functions, because you're writing a lot of functions like we're about to do today. What you're about to do today will be a lot of this kind of thing, where you're writing functions and you're passing Pokemon to those functions back and forth. You're passing moves back and forth, and you're changing and reading values of those things. Okay. This is the same idea, though, as I could pass a Bulbasaur, or I could maybe be working with Pikachu right now and changing his health because he took damage. Oh, Pikachu attacked Bulbasaur, so let me change his health, and I can change his health via here. So I could be like pointer to Pokemon. Something like this. Okay. All right, I want to go over the book exercises some more. There's one more piece. There's one more question here. So this one here required the book. So this was a good example of using an array with pointers. And this is demonstrating that you can do fun things with pointers and arrays, which we'll dive into a little bit today. But I kind of want to know if anyone got the answer to this. Did anyone ever actually, did you try? Yeah. You got the answer?
I think I got it.
Okay. So the answer here should have been 3 and 5, if you guys got it. So let's just go line by line and just talk about what's actually happening, because it looks like there's a lot of stuff going on. They're adding more and more symbols, and they're adding more, it seems like, complexity to it, so it's really important to go line by line. So the first line, if you read it, you'll see that it's declaring an array with 5 elements and and it has the numbers 1, 2, 3, 4, 5 in that array. So the array is the variable A has 5 elements. This is what's called a static array. It always had 5 elements in it. Then a pointer to an integer pointer called P1 is declared. Okay. And then it's setting that integer pointer to the memory address of the second index into that array. Okay. This is basically, hey, whatever's at this element in the array, give me the address of it. So what is the number that is at that position in the array? 3. How do you know that? Because it goes 0, 1, 2, so it's 3. So it gives you the memory address of what's right here, basically right here in memory. That's what it'll be. So if I put this in a spreadsheet, just going to put this back to the way it was. So A, there is no B. I'm just going to just do this for the sake of I'm going to do this like this, A at 0. It's going to be 1, 2, 3, 4, 5. Okay. So P1 currently stores, and I will color code these as well because we'll make a little rainbow. P1 can be purple. Okay. So P1 is currently pointing to A at 2, which happens to be this. Okay? Does that make sense? That's how it's currently arranged. So when you do C out this, it prints out 3. Right? So this right here is a little bit different. So I think some of you guys might have gotten, it's kind of weird. This problem should be set up a little differently. I want to see. I'm going to do by 2s. I'm going to change this program a little bit here because I think that the way it's set up is not really. Let's do this. Anyone off the top of the head know the answer now? It's different.
7.
It's actually 9. It's okay. Let me go over why that is. So, what does C out? What does P1 print out now? It should be printing out 5, right? That's what the value of it is. So let's go over this magic little piece right here. This is a special. This is a little special piece of C++ that is actually kind of commonly used. And the reason, so I want to explain give you a little bit of context as to why this is important for you guys to know. So something that's very common in games is save files, right? So you want to be able to save your game and write it out to somewhere on your disk, or save your game and upload it to the cloud, right? Or load a file from disk, whether it's a save game or maybe it's a level that you made. Let's say you go home and you're working on your game at home and you make a level editor. You need a way to basically be able to edit those things. Even if your level editor happens to be Excel, you need a way to write it out to the disk and read it in from the disk. And a lot of times when you're working with save game files, you are dealing with a huge just chunk of data. So a save file is generally just a file that lives on your disk that has a bunch of information next to one another, like piece by piece by piece. Whether it's like, hey, let's take for example a save file for Skyrim, right? It's like, hey, this is where the player was when he saved. This was his HP when he saved. This is all the items in his inventory when he saved. Here are all the things in his house when he saved. Here's the status of his quests. Basically just a bunch of numbers and strings and arrays and bools telling you in order what currently the state of the game is. what I'm about to show you is how you parse something like that. So usually when you load that file in disk, you actually have a pointer to the first piece of that save file, that first memory address of where that save file is. And oftentimes you need to jump around in memory in that save file to get to the pieces that you care about. Let's say you're loading that save file for Skyrim, and the first thing you want to do is restore his quest line. And what you have to do is, in that file, you need to go to the position in that save file of where his quest progress is. And the way you do that is what's called pointer arithmetic. So there's a way you can make pointers jump around relative to where they currently are. If a pointer is pointing to somewhere like here, you can make it jump down 2 spots if you want to, or 3 spots in memory. And this is what pointer arithmetic is doing. It essentially says, hey, take this pointer I have and move it forward or backwards some number of steps. So for example, what he's doing here is saying, hey, pointer 1, remember that's a memory address, set it equal to whatever pointer 1 is plus 2. This is actually special. This is not the number 2. So you have to think back to when I said pointers can only store memory addresses. They're special. They are not numbers. Which means when you do arithmetic with a pointer, this is not normal arithmetic. This is not number arithmetic. This is memory address arithmetic. This is pointer arithmetic, which means it's completely different from regular old adding. When you're doing addition and subtraction with pointers, you are talking about memory address addition and subtraction. Keep in mind, this is completely different than doing this. Okay? So this and this, these are 2 completely different things. This right here is adding the number 2 to whatever's stored at the memory address in that pointer. This right here is regular old arithmetic. That's just regular old add a number to it. If I did this, what does this give me? Does anyone know, like, if pointing to here, it gives you 7. If I do like this, what does that give me here? 105? That's what this line is doing. This is dereferencing the pointer before adding. That's fine. This is all hunky-dory. Everything's good. No problem. This is pointer arithmetic, which means it's not actually adding values. It's adding memory addresses. It's adding jumps in memory addresses. This is saying jump. And this is saying specifically jump down 2 spots. And specifically how much it jumps in memory is completely dependent upon the pointers in it. So actually I'm going to correct this here. Because remember that integers are 4 bytes each. So 9, 10, A, B, C, D. So that's the actual memory addresses here. So if it's pointing to this, and I say, hey, add 2 to it, what it's actually going to do is going to say, hey, go down 2 spots. So where does it point to next? Does anyone know? Can I guess? This one here, A4. That. It jumped down 2 memory addresses. How many bytes is that? Well, 16, it's actually 8 bytes. But here, let me just go over the answer. So what does it print out now if I do C out this now? It prints out 9, right? That's what this line right here is doing. It's saying move the pointer 2 spots. Okay. So when you're working with a save file and you're reading, typically save files have what's called a header. So a header is like a little piece of information at the front of the file telling you all the information about the rest of that save file. Like how long is the save file? How many quests has he done? How big is this thing? How many characters does he have? And that header sometimes has information about kind of like where you can jump the pointer to find the pieces of information that you need. This is especially important for things like level data. So we use this in Overwatch for things like when we build our maps in Overwatch, a big part of our maps is we place these things in the map that are special entities, like a control point, like an area where you can stand to capture the point. Destructible objects or crates are placed in level. Spawn points are placed in a level, right? Health packs are placed. So when we build that map, when you click save in our editor and you're like, hey, I want to play this map now, and I save it, the process of building that map includes gathering up all that data, condensing it, compacting it, and then dumping it out to a file that lives on your hard drive. Then when you go to say, hey, I want to play that map, that file gets loaded into your game. So Overwatch brings up that file. You guys ever wonder why there's like progress bars and why it takes a while to like load maps? So bringing that file in. And the first thing we do is like, okay, we have to kind of decide, and this is what game development is all about. How do we want to load this map? Like, what's the order in which we want to create things? So you want to be fast, you want to be efficient, you also want to make sure you're doing it correctly. So maybe it's completely up to us, our discretion. Maybe what we do first is we load all the geometry for the map. We load all the collision data for the map. So we'll grab that map file, which has all the collision data in it, and we'll maybe like, look, okay, tell me where the collision data is, because it might be anywhere in this file. So we'll take that, and then we'll find where to move the pointer. You can imagine like a little, almost like a record head that you're reading. You want to move it. You want to move this pointer to where you want to start reading. So you move it to where it is in the map, and then you start reading. You basically start reading memory from there to get you the collision data. And you read a bunch, and you say, okay, I'm all done with the collision data. What should I do next? Oh, maybe I'll create the spawn points. You read where you should go. You move the pointer to where it needs to be. So that's why this little guy is important, because understanding when you're doing pointer arithmetic versus regular arithmetic is very important. And this is very different from this. And keep in mind, in order to know, this is one of the tricky parts. This is why C++, I'm giving you guys a peek. This is why C++ can sometimes be really complicated. Because if I had deleted all this and just asked you what that's doing, you actually physically cannot answer what that's doing. You don't know. It depends on what P1 is, right? And this is why C++ can be sometimes a pain. Because something as simple as this equals this plus 2 means completely different things whether you're dealing with pointers or whether you're dealing with numbers, okay? That's why C++ requires you to read and have context. Like when I see this line in here, you might assume that's P1 adding the number 2, but you have to take a minute in your head and be like, wait a minute, is that a pointer? Like, I'm not sure. I need to know what this variable is. And then once you decide, oh yeah, okay, it is a pointer, that means that, oh, okay, he's doing pointer arithmetic. Then I can understand more. So C++ has a lot of these kinds of things, and I'm kind of like keeping them back as much as I can because there's a lot of things that kind of get tricky. Even something as simple as this, you don't actually know that that's going to equal 12. And this is one of the crappy parts about C++, because C++ has, it's kind of like, it's full manual control. You can do anything you want to with almost any variable type. Someone can actually say, hey, this right here, what that normally does, it doesn't do an assignment. It does something completely different. They can overload what those things do. They can overload what this plus does. They can change what that plus does. So typically you wouldn't do that. This would be a very bad thing to do if you change those. But that is something that C++ will let you do. Which is why if you ever read on like hacks and stuff and like shitty things to do before you quit your job kind of things, you'll see someone do, you can do things like
Yeah, show us exactly what you're doing.
I see you've already lifted
yeah.
Just in case.
You can do stuff like that.
It's an emergency.
I read some post about it. It's like this is kind of like a super evil thing to do. What this actually means is that, hey, anytime you were to use true in your code, anywhere where true is, instead there's a 1% chance that it will be false instead. That's actually this. So yeah, and like you could do this. What that means is that, you know, it's a very small percent. So like 99.999% of the time your program runs fine, and then every so often it'll crash or do something really weird. For that one thing, it'll just change behavior. And the problem is you would never know that this was happening because this could be put somewhere really hidden in code. This is the kind of stuff that you can do that will ruin your day.
So Keith, if you ever get fired and Overwatch just breaks,
You could say, yeah, you should search for that little bit of code to see if anyone does it.
oh no, there it is.
All right. Okay.
Graphics card is like.
So let's go over the answers to number 7, 8, and 9 in the book, and then we'll do a lecture today. Any questions on that stuff? So yeah.
Why does this work when you put it in C++? Why does that give you the 3 and 5 instead of?
Because it just so happens that 3 plus 2 is the same as the memory address that's pointed to by 3, 2 spots up. They're both equal to 5. So that's why I changed it to 1, 3, 5, 7, 9. Yeah, it's kind of a weird example.
I have a question.
Yeah.
For the array, is there a physical account of the memory address for the entire array, or does it?
No, that's actually, no, arrays don't work like that. Arrays work exactly like this. There's no, the thing that's pointed to by array is always, this is where it starts. That's where the array starts, and if you had to have a pointer to an array, it would be here. It would be the first element. So, yeah, for example, for here, if I wanted a pointer to point to an array, you could do, I think the book actually talks about it. You can do that. And what this means is point to the array A, which actually means point to the array at index 0. Yeah, arrays are very similar to pointers, but I'll talk about that later. Okay. So the book, there's 3 problems in the book that I want to have you guys do. Number 7, this guy, William Wingate, runs a pizza analysis service. For each pizza, he needs to record the following information, which is the name of the pizza company, which can consist of more than one word, the diameter of the pizza, the weight of the pizza, and we need to devise a structure that can hold this information and write a program that uses a structure variable of that type. The program should ask the user to enter each of the preceding items of information, and then the program should display that information using cin or cout, or cin and cout. It's basically asking, write a structure, and then put data into that structure. Okay. So I'm going to go through this first with writing a very simple main. This should be kind of the very first thing you write almost every time. Just do this, compile and run. Make sure you have typed in those things. So we need a structure that can hold information about the pizza company. So it's also how big the pizza is, the diameter, and the weight. So in order to declare a structure, the syntax is the word struct followed by the name of what you want to call your structure, and then set a curly braces with a semicolon. And there are 3 pieces of information which they care about. One is going to be a string, so we're going to do that. So the first thing is going to be the name of the pizza company. So I'm just going to call it name. The second is going to be a diameter of the pizza, which I'm going to use a float, and then the weight of the pizza. So structure lets you kind of declare, as this is for variables specifically, declare variables that live inside of it. And we're going to be using this today for our Pokedex example. So name, diameter, and weight. And it's asking to say, hey, write a program that uses a structure variable of this type. So we need a program that asks for a pizza company. So I'm going to create a variable that stores the pizza company. Let's call this company, I don't know, Papa John's. So what we need to do, or we don't actually know it's going to be Papa John's. I'm just going to say generic company, because we're going to let the user decide. So the first thing I'm going to do is ask for, hey, enter the name of the company. Okay. And we're going to do a cin. So how do we actually plug that name of the company into this variable? So this variable is a structure, which actually means it's made up of several variables. And so from the book, you do that. And this will work fine for a single word name. I'm going to show you guys how to do this for more than one word. I'm just going to do, I'd like to do a simple thing first. So this is the way that I work is I like to do like one little piece at a time. So enter the name of the company, do this. And maybe I can do a standard cout generic company.name just to see what happens. Get a dummy variable here. I'm just going to run with just this. Oops. So I'm just going to type Papa John's, one word here. And it prints it out again after I'm done. Cool. So I know that that works. What I can do now is ask for diameter, and I can ask for weight. So whenever I have to do multiple things, it's always kind of helpful to do copy-paste because it saves you a lot of time. So you can say enter the diameter of the pizza. You can do this. Diameter. And this is going to be enter weight of the pizza. Okay. And all we're going to do is we're going to print out the name, the diameter, and the weight. And let's put ADL. Again, I'm copying and pasting here. So now I'm printing out the weight, name, diameter, and the weight. And let's just do this. All right. 12.0 and 512 pounds. Pizza company information. There's Papa John's, 12 and 512. And we could do a little bit better. We could do name. And we could do diameter. And weight. Okay. Here's our pizza information. So the book asks you to support entering multiple words for the name. So the way that you actually get a single string into, get multiple words into a single string is you can't actually do this because this will actually only let you enter one word like for that string and then it'll stop taking input. So what you actually do is there is a getLine function that you can call that takes two arguments. One is going to be where you're reading the input from, and the other is going to be where you want to put that information. And this little guy here will read an entire line at a time, so you can enter multiple names. This is there's also a caveat to this, which I'm going to talk about in a little bit. But now that I've done a get line, I can do Papa John's Pizza. So you can see here, you can type in however long you want to, and that works fine. Some of you guys might have run into a problem. If you do this, anyone run into this issue where it was like eating some inputs? I'm going to do diameter first, 512, and then what happened? I didn't even get a chance to enter the name of the pizza. So this is highlighting one of the ways, the kind of the interesting ways that cin works. So the problem here is that when I type in the diameter, that's fine. The weight here, I'm going to push the enter key. What actually happens is that when you push the enter key, there's a magic little character that gets left in the input buffer for the computer, and that magic character happens to be the new line character. And so what happens is that, oh, I hit enter. And it's like, okay, well, that's still in the buffer. It hasn't been read yet. Then when you go down here to asking for the name of the company, it's like, well, I already have something here from the last time you asked for input. I'm just going to use that instead. And it's just going to use that new line, and it's going to eat that and say, okay, I guess this is all you want to enter, and then it's going to move on. And so it doesn't even give you a chance to enter it. So what you need to do in order to solve this is anytime before you call getLine, if you have a cin before it, right after the cin, you actually want to do a cin.ignore. And what this guy will do will be to eat up that enter key press so that this thing can function properly. 12, 512, and now I can enter. All right. So that's number 7. Questions on this? All right. Next, it asks to use new to declare a structure instead of declaring a structure variable. Also have the program request a pizza diameter before it enters a name, so we just did that. So they want this to be a pointer. So what happens when you use a pointer? And this is also part of the book that you had to read. Well, we went over this. If you want to declare a pointer and you want to use it, let's do 2 things first. Notice all these little red squigglies now showing up under these. Why is this a problem?
Because in the first one you put a stop, or no.
This is a pointer now. So
There's no value.
Yeah, it's not maintained.
well, yes, it isn't pointing to anything. You're right. But the problem with the red squigglies is this little guy right here. This little dot operator right here. So why? So let me talk a little bit about why we're using the dot operator to begin with. What does this actually represent? This means get this variable that lives inside this structure. That's what this little guy does. And anytime you type the dot, you notice you get these little pop-up things. So when I have this is fine for that. But when I'm working with a pointer, it would be great if it just figured out. I don't know why. I actually don't know why C++ doesn't let you just use a dot. Because this doesn't even compile. So the weird part is that when you're using pointers and structures together, you can't use a dot. That's the only reason you can't use a dot. There's a different operator that you have to learn, and this is just how C++ works. There's an operator called the arrow operator, which functions exactly the same as the dot, pretty much, but it's only used for pointers. So if you have a pointer, you have to use an arrow instead. This is called the membership arrow operator. It means, and this is basically the membership dot operator. So use the arrow with pointers and use the dot with non-pointers, and that's the only difference. Okay? And anytime that you do this, and this is not the last bit, there's one more piece we need to do. So if you guys try to do this right away, it's going to crash. Actually, it won't even let me compile this, which is interesting. If it would let me compile this, this would crash. So how do pointers work? So the reason why pointers are, it actually says we have to use new to allocate a structure. So I have this pointer to something called a generic company. I'm going to make this thing bigger. I'm just going to delete all these for now. Okay. So there's a memory address of generic company. I declared it. What is the value that's in generic company right now? In my code. So if you guys remember what my code looks like, what is the value of generic company? What memory address is it storing right now? It's not storing anything. So it actually has nothing in the memory address. So it actually, that pointer doesn't point to anything right now. So when you say, hey, put something in the diameter of this, it's like, well, I'm going to try to find out what's at this memory address here. Looks like this memory address here is empty, boss. I can't do anything with that variable. There is nothing here. Yeah. So this is why it's important to call new. When you call new pizza company. Okay. What this little guy does is he goes and he fetches memory for me. Remember I talked about this last week too? So he's going to create memory for me, and he's going to create memory for these things: name, diameter, and weight. So name, diameter, weight. So I'm going to do this. Some number. I'm just gonna pick memory addresses here. Color code these guys again.
Ate a little too much chili yesterday.
Totally worth it.
It's all natural.
For always, man.
It's like a waterfall.
So what new does is it goes back and says, hey, I need memory for these things. Cool. So it goes new causes this to happen, and then when you're saying, hey, equal to new pizza company, it's going to get the value of that first thing in that structure. And this is kind of a little bit weird because a pointer to this structure here is going to point to, I'm kind of faking the memory addresses here, but it's going to point to the variable that stores. Maybe this is a better way to do this. I'll just do this. I'll just leave it like this for now. I don't want to get into the discussion of exactly what happens, but this stuff here, this memory, gets allocated. There's a chunk that goes and returns you back the pointer to that memory address. So in this case here, I happen to be pointing to the name, even though this whole thing is a structure. So this whole thing is a pizza company. And pizza company technically is this, and these little guys just happen to be inside of it. Can't go any smaller than that. Okay, so these two happen to be the same memory address because that's what the structure has. So this is actually pointing to the pizza company here. Okay. So what are the values of name, diameter, and weight right now? These are all also empty. Empty, empty, and empty. So as I enter in each of these pieces of information, the diameter and the weight, like diameter is 12 and the weight is 512, and the pizza company is Papa John's. So each of these things lives inside of the structure, and the pointer is still pointing to this guy right here. So when you go to print them out, you print it out by using the arrow operator like this, just like you would a dot operator, and that'll get you the name that you put in here, making sure that you call delete on generic company afterwards. And this will look exactly the same as the regular program. Like so, nothing different. It just happens to be using a pointer here. All right, questions on this? Okay. So number 9 was kind of based on number 5 and 6. So a lot of this stuff was actually similar to the pizza company. It was a little bit simpler. The key was that there's a candy bar structure, and it's asking for basically the same thing, the name, the weight, and the number of calories. So asked to create a program that initializes that variable. And then the number 6 was saying, hey, pre-allocate 6 things instead of asking the player for them. So let's just go over this. And I'm going to write out this candy bar program because this is a great example of using more examples with structures. So we're going to call this thing a candy bar. And it's asking for 3 things: the name, the weight, and the calories. And it's asking for candy bar snack, and saying snack dot name equals mocha lunch. Snack dot equals 2.3. $2.50. Number 5 was asking you to do this all in one line. So this is one way you can initialize it. Remember, you can also do this. This is the same thing, like so. These two are the same. So I'm going to show it like this. This is how the book has it. And then it just does snack name, weight, and calories. So you should just print out Mocha Munch 2.3 and 350. All right. Okay. Number 6 was just create an array of structures. So we're going to call this one snacks. We're going to have 3 elements inside of it. So if you want to initialize these guys in an array, you can actually do that inline as well. So you can do this like this. And this is a little bit, I find this to be a little bit hard to use, but you can do it like this too. So I can call this one Butterfinger. This one could be Snickers. Did you use that?
Exactly.
Oh, really? I think those are the most common candy bars that come to my head. Easy to type too. So printing out this is easiest when you're using a loop. So I'm going to loop over this 3 times. I don't know, but it sounds good. I would eat it. So this I'm just using an array. All right. So there's our 3 candy bars here. So that's what the program number 6 was asking for. And the key was that here is asking for us to use an array that's not statically initialized like this, and then declare this as a pointer. So what I'm going to do is I'm going to break this apart. I'm going to say snacks equals new candy bar. And I'm going to create 3 of these guys. And then the way I'm going to initialize these now is going to be a little bit different. It's going to be like this now. Oops. Snacks at 0.name. Snacks 0.weight. And this is very similar to how we're about to do this for the Pokedex. So calories. So I'm just rewriting this a little bit to match what needs to happen for a dynamic array. So this is allocating an array of 3 entries into my pointer. I'm just going to do this 1 and 2, and this one's going to be Butterfinger, which had 2, and this one's going to be Mocha Munch. Snickers, 4.3 and 550. So this is most of the work, was to allocate an array and then initialize each element separately like this. This loop works exactly the same though, which is nice. And so this output here will give you exactly the same output. Okay. All right. And just to give some context as to why this is useful is because when you allocate like this can be something that you input. This can be something that you ask for how many you want. So you don't have to decide this up front. You can decide this later. All right. Okay, so that's it. Let me grab all the homework off of here. Week 3. All right.
I learned a lot about fish.
So we are going to jump ahead to chapter 7 now. We're going to be, if anyone wants to follow along, we're starting on page 313. We're talking a little bit about functions and structures, as well as functions and pointers. Because the goal is that, again, remember the goal of the class is we're going to be making a version of Pong. In order to write Pong effectively, you're going to be using pointers and you're going to be using functions quite a bit. So let's go over this a little bit more in detail.
What page was it?
This is page 313 in the book. Let me just So structures are really important. We've been using there's like examples for candy bars and stuff because it lets you combine multiple variables into a single one. In fact, structures are really important because they're actually very similar, if not almost completely identical, to another C++ idea, which are called classes. We're learning about structs right now, but when we learn classes in the next class, C++ class, we will be learning about how to use some of the more advanced techniques of C++ to make kind of more, not advanced games, but more cleaner, easier to work with games, and it will simplify your work quite a bit. And one of the goals of C++ is to make your work a little bit less repetitive and to remove things that remove blocks to your workflow, so that when you're working with something like a very large code base, you don't get lost in the little details. You're working efficiently. You're not getting caught up in doing things over and over again too often. So we will be talking about structures and pointers. So let's use I'm going to use candy bar, not as the example here. I'm going to make a brand new file. So up to this point, we've been using functions with parameters. Like if I create an example, we made a function that's like, hey, you guys remember the roll die function, which takes an integer num sides, right? So here's our roll die function. I'm just going to I'm going to use this roll die function as our example because we're going to return to an integer. And we're going to return rand this modulo num sides plus 1. This is basically what we did in lab the one day. I'm going to roll d20. And this is more of a lecture. You guys are free to follow along too if you want to, but I'm just kind of I'm writing this stuff out so that we have something to work with. So every time I run this program, it's going to roll a die. So there's a d20. I got 11 there. I got 4, 11, 7. So there's my d20 function here. So the best part about structures is that you can make anything into a structure. And one of the things I like to make into a structure here is our dice. There's nothing that says you can't have a abstract concept like a dice roll be put into a structure. For example, oftentimes in D&D or in games, you'll have to roll more than one dice, right? You'll have to roll multiple dice. And if we have the concept we can create a structure called a dice roll, which is going to represent you basically holding like dice in your hand and rolling them out onto the table. So what we can do here is we can create a dice roll, and there's going to be two properties to it. We're going to have the number of sides of the dice, just like what we have here, and we're also going to have another number, which is going to be number of rolls. How many times we want to roll that dice. And this dice roll here is a structure that basically combines a dice roll. Let's say I want to roll 10 d20s, and I want to roll 6 d4s. All right, that's what our dice roll includes. And this is kind of like a damage roll that you might have in Pokemon or in Diablo. So if I want to set up a dice roll for my, I'm going to call this one this is going to be my damage roll, and this is going to be my dodge roll. I'm going to create a dice roll. I'm going to call it my damage roll. I'm going to set damage roll num sides to be equal to 20. There's going to be 20 sides to this dice. And the number of times I'm going to roll it is going to be 10. I'm going to roll this 10 times. My dice roll for dodge. The number of sides is going to be 4. And the number of rolls is going to be equal to 6. So I have this structure, and what I'd really want is just to be able to write something that says, hey, rolling 10 d20s, and then print out what the result of that is. So if I were to be able to use this dice roll, what I can do is, why don't I make a function that's called roll multiple dice that takes a dice roll. I'm going to call it dice roll information, or dice roll info. I can create a function prototype that takes a structure as a parameter, just like any other function. Instead of taking a single value like integer, I can take multiple. So this function, which rolls multiple dice, takes a structure, which I'm going to implement down here. And all it's going to do is I'm going to write a loop. I is less than dice roll info. I'm going to roll it num rolls times. And then for each of the times that I roll, I'm going to create a variable that starts at 0, and I'm going to add the result of my dice roll every time. And then the number of sides that it has is in that structure as well, like this. And then finally, I can just return the result. So this function here uses dice roll info in 2 places. It lets me take whatever they pass in and grab the number of rolls and the number of sides off of it and return the result. So when I call my function here, I can call roll multiple dice. And all I have to do is pass in my damage roll here. And this is the key right here. This is what I'm passing. I'm passing a damage roll, rolling damage. And I'm going to do it again, this time passing in my dodge roll, rolling dodge. Because that function takes a structure as a parameter, you can see the output here. This is 10 d20s, and this is 6 d4s. That function works with just a structure. So let me show you what this looks like in code here. So I'm about to call roll multiple dice. So my little yellow arrow is here. So I'm going to pin this guy here. You guys probably can't read that, huh? do this again. Oh, it broke my... I'm just going to use the magnifier. Okay, let's look at the top there. That's what structures look like internally in the C++. Has a variable called dice roll info in my function, and it has two variables inside of it, one for the number of sides and one for the number of rolls. So this function is able to use both of these numbers here. How many sides I want a d20, and how many times I want to roll, 10 times. It's able to use this inside this function here. Now, you might be wondering, why would I use a structure here instead of just writing a function that takes two arguments? You could write a function called roll multiple dice, which takes sides and it rolls. You could do that. And it would work almost exactly the same. This would be sides. This would be rolls. And this works fine because I only have two arguments. There's a couple reasons, though, why structures are really useful. One, when you add new variables to the structure, you don't have to change the function. So for example, if I wanted to say, hey, add a int bonus roll chance. And let's say I also want to give it a name. If I want to have these two things in there, I couldn't really add them easily to here without actually adding them to the list. And every argument that I add to this function parameter list makes that function that much longer, which also makes it a little bit more tricky to use and call, because now when I call this function, I have to pass in all four arguments instead of just the one. So yes, you can separate out the variables like this, but this gets to be difficult when you're adding more. Another reason, and this is the kind of the more important reason, is that when you're passing in arguments to functions, it's actually not free. So free meaning it's actually not, it takes work from the side of the computer to set up a function call to do it correctly. So what do I mean by that? So when you call a function like roll multiple dice, and let's say I'm just going to make up a bunch of variables here. I'm just going to copy and paste a bunch of these like this. Let's just say I had, I don't know, some random variables like numsides 2, 3, 4, 5, 6. Not that it would ever do this, but this is a good example. As we mentioned, structures and variables in C++ take up memory, right? They take up space in RAM to represent that data. And one of the things about calling functions is that when you call a function and you pass it, this is a perfect example here. I'm calling this function roll multiple dice, and I'm passing it my damage roll. When you get to this line of code, so I'm going to run. I'll put my breakpoint here. My little yellow arrow is there. When I step in and I go to this function and it's down here, what the program is actually doing behind the scenes is it's taking all the data that was in the original variable here, this damage roll. It's taking all that stuff. It's making a copy of everything inside that structure. Meaning it's taking all of the stuff that's inside of this structure, making a duplicate of it like you copied and pasted a file in Windows. And then it's putting all that stuff right here into this variable. It's making a copy of every single one of those variables. And one of the reasons why this is really important to understand is that this is understanding when it's doing this and when it's not is one of the keys to making high-performing AAA quality games, right? So understanding when you're paying this cost of copying a huge amount of memory and calling a function, this is what separates like kind of the beginning software developers and the more like, you know, the mid-level and senior developers, the guys that understand how memory works, is because this kind of thing has to become kind of second nature, because this cost is not free. And it seems like such a little thing. Like, my computer is super fast. It didn't take any time at all for me to go in there. You can't even notice that it's taking up any time at all. But you do, if this function gets called hundreds of thousands of times, or millions of times, and I guarantee you we have functions in Overwatch that are called hundreds of thousands, millions of times, that have parameters passed to them. You have to understand that those things add up over time. Those are the kinds of things that make your game run at 40 FPS instead of 60 FPS. Or make your game run at 20 FPS instead of 30 FPS. And when your game like doesn't run well, or it feels sluggish, there's a lot of things that happen. One, not as many people can play your game. So one of Blizzard's philosophies is that, you know, we want to make sure that gameplay is first, and part of making gameplay first is that the game should be fun to play for as many people as possible. We pride ourselves on making our games run on a wide variety of hardware, so people that have like 7-year-old PCs can play Overwatch. And one of the reasons why that is successful is right here. Like this right here, passing parameters to functions and understanding what the cost is why Overwatch can run on older machines. I guarantee you, if we didn't care about this kind of stuff, like about the cost associated with calling functions and making it be expensive like this, the game wouldn't be running 60, or it would be only running on 60 on more higher-end PCs, so you'd have to kind of buy or upgrade your PC just to be able to play it effectively. So understanding that there's cost here is really important. Like, it went through one at a time and said, okay, grab whatever's here and copy it. Grab whatever's here and copy it. So let me demonstrate this in this example here. I like using a spreadsheet because it makes it a little bit more clear for me. So I'm going to have a variable here called damage roll. It lives at this memory address. And it has a bunch of variables. Like, I'm just going to say I'm just going to have it be A, B, C, D, E, F, G. We already know the memory address is here. Sure. I'm going to color code this guy. More rainbows coming. And I want to demonstrate this because I'm going to slow down what actually happens inside the computer, slow enough to understand why this is so important. I'm going to create a structure that has A, B, C, D, E, F, G. I'm just going to call this A, B, C, D, E, F, G. So there's our variables here. I have A, B, C, D, E, F, G. So I have A, B, C, D, E, F, G. And maybe these values have like 2, 14, I don't know. I'm just creating numbers here. Maybe one of these things is a string. Maybe one of these things is a bool. Maybe this one is a really large number. Maybe this thing here is I don't know, character. So when you call a function and you pass in a structure that has those variables, what it actually has to do, again, is take each of these things and create a copy of it and put it in another variable. So temporarily what it will do is when you call that function, it creates another set of variables down here. Okay, called 7, 8, so what it will do I have to do these by hand. Okay. So when you call that function, the first thing it does is like, okay, well, what do I need inside that function? I need this guy here. So let me go here, copy this guy, and paste him down here. Okay, let me take this guy here, copy him, put him down here. Let me take this guy here, copy him down here. This guy here, copy him down here. This guy here, copy him down here. This guy here, copy him here, and this guy here, and copy here. Okay? And I call that function, and when he's done, he deletes all this stuff. It's all gone. Then when you call that function again, he has to do that thing all over again. All gone. Take this guy, copy him here. Take this guy, copy him here. Take this guy, copy him here. When I say he's copying into this temporary thing, what I mean is inside this function, this variable here, this dice roll info, is where he's copying the variables to. He has to build up this parameter based on what's called to it. And that takes time based on how many variables are inside of it. Like so. And doing this every time adds up again. Which is why when you have something with a lot of variables in it, it can sometimes be really expensive. One of the most common things that get passed around are in games is vectors. And a vector in a game is a position, it's a coordinate, it's like either a coordinate or it's a point with a magnitude. A vector is a structure. Maybe it has 3 coordinates to it. It's pretty much an x, a y, and a z. This is one of the most common things that gets passed around. This usually represents a position. Everything in 3D games is represented in an x, y, z space, like horizontal, forward, and up and down, where you are in space. Velocities are represented by this. We're going to be using this at Pong. There's a 2D version of it, which guess what only uses x and y. But again, you still pay this cost of copying it around if you call a function and pass this in. So I want to say this is important because normally you think, okay, well, that just means that how do I work around it then? You have to pass stuff like this around. Some of our variables are some of our structures are huge, like huge. One of our most common structures, which we use to store movement information, is like hundreds of bytes, like very relatively large. We pass that thing around everywhere. Everyone has to know movement. We use movement information for where you are, how fast you're moving, what you're standing on, whether you're jumping or not, what you're animating, whether you're currently crouched, whether you're currently grappling. We have all this information in the structure, and we're throwing it around everywhere. But I said earlier that if you just pass functions, parameters like that around, then your program tends to run slowly because you have to copy it. So how do you work around that? This is where pointers come into play. Remember when I said that pointers store memory addresses? That's all they store, right? That's the only thing that they store. And up here, I have this set of memory addresses here. If I had a pointer that pointed to A, I could figure out where the rest of B, C, D, E, F, and G are. And if I could do that, all I would have to pass around would be one memory address. I don't actually have to pass around the whole thing. I don't have to actually copy everything, right? So if I write this function, take a pointer as an argument, like this. And I go down here, I change it to be a pointer. I change this because remember you can't use the dot operator, you have to use the arrow operator. And here, if I change these equal to new dice roll, like that. Oh yeah, thanks. Like this, same thing, I just create a new dice roll. And I pass it in here. Now what happens when I call that function is it doesn't copy every piece of info inside that structure. All it copies is the pointer. So for example here, if I go back to my spreadsheet and I go back to my example here, and I have a variable called dice roll info, and it lives at, I don't know, 0, 7, 1, 2, 3, 1, 2, 4. And I store the memory address here, like that. When I call that function roll multiple dice, and I'm passing it a pointer, all that it's copying, when it copies, is like, well, I still have to copy, so I'm going to make a copy of this. I'm going to put it here, I don't know, 9840. I'm just going to copy this one, and that's it. That's all it copies. It just copies the memory address. Because that's all you need. You just need one little piece of info. And this is pretty much like as fast as it can be. Like compilers and programs are optimized to pass memory addresses around like this, like little pieces of information like this. If I do this, if I pass a pointer around, it doesn't matter how big this variable is. It doesn't matter at all. It could be gigabytes of data. And all I'm passing around is a little tiny piece, a little tiny number that's just where that data starts. And I can use that to speed things up. So to do this, I have to declare a pointer variable, right? Not always, though. There's actually one more way. Does anyone know how I can get the memory address of something to pass it into here? How do I convert something that's not a pointer into what a pointer knows? Like, how do I convert this into something that a pointer can be used? Ampersand? So if I do this right here, it's exactly the same as if I declared a pointer like this. So these are the two ways you can pass pointers to a function that's expecting it. When a function needs a pointer, well, you could create a pointer and you can pass it to it. Another way you can declare a pointer is, well, the function needs a memory address. I have a memory address here, so I'm just going to pass it the memory address of that variable. And these both give me the same result. Same thing. All right, let's take a break, and then we'll come back and I'll give you guys a lab.